DevJuniors. Ever wonder how a character in Mario, Sonic, or even Cuphead knows exactly which animation to play and what actions are allowed at any given moment? The answer lies in a simple but brilliant structure. The state machine. A state machine is basically a model of computation. In games, it tells a character that, at any given time, it can only be in one of a finite number of states, like idle, running, or jumping, and never in between. This is why you'll often hear it called a Finite State Machine, or FSM for short. It's the blueprint that defines a character's behavior. Think of it like a set of rules. If you're in this state, you can only do these specific things. It's what stops Mario from swimming in the air or Sonic from running while he is jumping. The FSM keeps everything in order, ensuring the character acts predictably and makes sense within the game world. So, how does it actually work? A finite state machine has three key parts. First, you have the states. These are the distinct conditions your character can be in. A state is what the character is currently doing. For example, a character could be idle, running, jumping, attacking, or even invincible. Each state has its own set of rules and behaviors. Second, you have transitions. These are the pathways from one state to another. A character can't just magically switch from running to jumping. There has to be a defined path, a transition that allows this change to happen. You can think of them as one-way streets connecting the different states. And third, you have events, which are also called triggers. These are the conditions that activate a transition. An event is the why behind a state change. It's the specific thing that needs to happen for the character to move from, say, the idle state to the running state. Most often, this is a player's input, like pressing a button or moving the joystick. Let's build a simple example. Imagine our character starts in the idle state. They're just standing there, maybe with a little breathing animation. Now, if the player moves the joystick forward, that's our event. This event triggers the transition from the idle state to the running state. Now our character is running, and while they're in the running state, they have a whole new set of rules. For example, maybe they can't perform a ground pound attack while running. The FSM dictates that if the player then stops moving the joystick, that's another event that triggers a transition back to the idle state. See how clean that is? One action, one state change. Now let's make it a little more complex. What about jumping and getting hit? If our character is in the running state and the player presses the jump button, that event triggers a transition to the jumping state. While in the air, the character is locked into this jumping state. They can't just start running again mid-air. The only event that can typically get them out of the jumping state is another event like touching the ground. Once that happens, a transition takes them back to either the idle or running state, depending on whether the player is still moving the joystick. But what if an enemy hits them? We can create a hit state. This is a special one. We can draw transitions from almost every other state idle, running, jump and all, pointing to the hit state. The event for these transitions is contact with enemy. So, no matter what you're doing, if you touch a bad guy, bam, you're forced into the hit state. Your character plays a hit animation. Maybe it becomes briefly invincible, and then after a short time or another event, transitions back to the idle state. The real beauty of the FSM is its modularity. All the code for the jumping behavior is contained within the jumping state. If there's a bug with the jump, like the character isn't landing correctly, you know exactly where to look in your code. You don't have to search through a giant, messy file. This makes organizing and debugging games, especially massive AAA titles, so much easier. Developers can look at a simple diagram or a table of states and instantly understand the character's entire logic flow. This exact logic is used everywhere in the games you love. Mario's invincible star power. That's a transition to an invincible state with its own timer and rules. Sonic's spin dash. That's a charging state that transitions to a spin dashing state when you release the button. And every single attack pattern from the bosses in Cuphead. Each one is a different state in the boss's FSM, cycling through them to create those challenging, memorable fights. It's the absolute backbone of character behavior. So, the finite state machine is proof that sometimes the simplest solutions are the most powerful. It's your first major step toward mastering game AI and creating characters that feel responsive and alive. It's an elegant way to manage complexity, and once you see it, you'll start noticing it in every game you play. What's your favorite example of a state machine in a game? Let me know down in the comments. If you enjoyed this breakdown, please hit that like button and subscribe to DevJunior_ for more deep dives into video game algorithms. Thanks for watching.